Assalamualaikum and a very good morning. My name is Puterisarah binti Muhammad Saad. So I will be presenting this paper entitled Dynamic Effects of Illumination on Single Diode Photovoltaic Models, Performance Differences Between Indoor and Outdoor Environments. We are from the School of Electrical Engineering, College of Engineering, UiTM Shah Alam. So this is the outline of my presentation. So I will start with the introduction, introducing to you the single diode model solar cell used in this work. Then moving on into the problem statement, the objective of this work, the results and discussion, the conclusion, the references, and last but not least on the acknowledgement. So as an introduction, so the growing global demand for clean and sustainable energy sources has driven photovoltaic systems to be the forefront of the renewable energy alternatives. PV systems with the ability to convert solar into electricity play a critical role in lowering greenhouse gas emissions and mitigating the effects of climate change. Understanding the complex relationship between lighting and PV performance is critical because it highlights the efficiency, consistency, and overall viability of solar systems. So this is single diode model solar cell. So single diode model is a mathematical model that describes the behavior of a PV cell or module under different illumination conditions. So the model can be represented as a single ideal diode with a current voltage relationship described by the Shockley diode equation. So the model can be seen as in figure 1. So the model considers the effect of temperature, irradiance, and other parameters on the performance of the PV cell. So the current focus of single diode model research is on designing models that accurately predict the performance of PV systems under both indoor and outdoor lighting conditions. These include creating models that can account for impacts of shadowing, reflections, and other factors that affect PV cell performance under various lighting circumstances. For the problem statement, previous research has provided insight into the impact of lighting on PV systems, but comprehensive studies including both indoor and outdoor settings are still lacking. This study fails that need by adopting a thoroughly established experimental establishment informed by innovative field research. So the dynamic interaction between lighting and photovoltaic performance has significant implications for both indoor and outdoor PV system design and optimization. The objective of this work is, the first one is to simulate the single diode model of a PV cell in a solar system simulator in MATLAB. Second is to analyze the effect of illumination in MATLAB for both indoor and outdoor condition using SolarX MSX60 PV panels. So as for the methodology, so SolarX MSX60 was used in this work. So this module has been used as a representative indoor and outdoor PV panel for the evaluation of the power estimation methods. The SolarX MSX60 was chosen due to it being recognized for its comparatively high efficiency when compared to other solar panels available at that time. So it is able to convert a sizable part of the sunlight it received into electricity. So SolarX was also well known for creating dependable and long-lasting solar panels. So for a single diode implementation, so MATLAB Simulink was used to create the block parameters of IPH, IS, and IRS. So the output of the first subsystem will be IPH and IS. The required input was then added to the panel's input labeled as sub after the panel output was set up using the value of IPH and IS. So the connection was then linked with the ID1 and ISH block parameters to build the next subsystem. So this is the solar panel of single diode model. So as can be seen in figure 3, this is the simulation circuit of single diode model. So this is the global simulator for the simulation circuit used to generate the IV and PV graphs. So the global simulator connects all of the parameters and equations needed to design a PV cell system. So the precise connection of the parameters and equation will result in the correct IV and PV graph characteristics. So this is the adjusted value of irradiance as shown in figure 4. So all of the parameters adjusted as in figure 4. First, the parameters can be adjusted based on the condition of the illumination. Then the outdoor conditions, so like radiance of 200, 400, 600, 800 and 1000 watt per meter squared was set to observe the output. Second, the illumination condition, it depends on the light wavelength of the color. So however, the conversion of the sun is roughly around 0.08 watt per meter squared per lux. Therefore, this 100 lux, 600 lux and 1000 lux were multiplied with 0.079 watt per meter squared to get the exact value of radiance in watt per meter squared. So this is the results and discussion. So as can be seen, you have figure 5 and figure 6. Figure 5 shows the IV curve at different irradiance, while figure 6 shows the PV curve at different irradiance. So it can be seen that the current decrease when the irradiance is set at a lower value. So when the value of irradiance is set lower on the PV graph, the value of the maximum power estimated of the peak of the y-axis decreases as well. So while all the parameters are constant, it can be said that the higher the radiance, the higher the output current, and hence the higher the output, the power being generated. So figure 7 and figure 8 shows the IV curve and PV curve at low illumination in indoor condition. So the graphs for 200 lux, 400, 600 and 800 and 1000 in indoor conditions appear similar because the values of from 200 to 1000 only vary minimally when calculated in watt per meter squared. As you can be seen, it shows insignificant changes for all the illuminations value. Okay, this slide shows to you the performance of indoor versus outdoor. So for IV current values, all of the reported outdoors results appear to be better than indoor results. Same goes for PV characteristics. It shows that PV for outdoor conditions is better compared to indoor conditions. So the reason might be outdoor conditions give better performance due to outdoor environments often having higher levels of sunlight intensity. Another possible reason is that the indoor lighting sources frequently have a relatively uniform spectral distribution, which may be optimized for human vision. So when compared to outdoor sunlight, this would minimize spectrum variation and can result in fewer wavelength-dependent effects on PV performance. So as a conclusion, the single diode type of PV cell perform better under outdoor illumination conditions with irradiance varying from 200, 400, 600, 800 and 1000 watt per meter squared than under illumination conditions. However, when the sun irradiance varies, each condition exhibits an increase in current and also power. This is the references. This project was financially supported by the MIRA Research Grant Scheme under UiTM Internal Grant Scheme. Also, we would like to thank the School of Electrical Engineering, College of Engineering, UiTM Shah Alam for providing laboratory facilities and financial support. With that, thank you.